x and this one x1. Because as a matter of fact, this one is also moving at theta. So we won't need this one actually. But we can model it. And then we move it. Right. So let's now write our constraints. We know that in circular motion, if you've got a radius r, and this is your arc described, and the angle, the relationship is arc, maybe S for arc, is equal to r theta. Okay? We know that already, ne?
Yes.
So let's use this. If we take theta and this x, let's call this for now L, and this one L over 2, for the purpose of that of our derivation. We know that L is equal to 1, L over 2 is equal to 500. We know that. But we don't want to write these long figures and long things. We want to write simple things. So we are going to say x1 is equal to L theta is our first constraining expression. Then we are also going to say x is equal to L over 2 theta. Always do that. Even if your book doesn't say so, it's because they don't like it. They will do it without saying it. But if you do it, you are organizing your work and you are making it very simple. Okay? This is L with the angle. So x at L becomes what? X1 at L becomes x1 is equal to L theta. Similarly, this is at L over 2, our x. So x is equal to L over 2 theta. If you could go on and do even the what? The first derivative, the second derivative. So your first derivative, if you wanted, you were going to say x1 dot the velocity at that point is equal to L. L is a constant, so it doesn't, it remains as it is. But theta is a variable, theta dot. Okay? And similarly, x1 dot dot, which is the acceleration, is equal to L theta dot dot. Are we together? In the same way, you can do the same for that. So we are not going to show that, but that's what it means. Now, let's now write our expression. And we are taking moments about the pivot, which is here. Let's call this O. So if we take moments about O, we are going to say from this expression, that will be our what? Acceleration moment. So it's well defined for us, so we can simply say acceleration moment is equal to I, we call this point O, I naught theta dot dot. That's our acceleration moment. Now we want our restoring moment. What is causing restoration? The spring which is positioned here at X. First of all, if we are to find, let's call this K, let's call this M. We first use the symbols. Always try to first use symbols. Because if you use values and you miswrite your value, then you've written something wrong. Let's say you make a mistake, you wanted to write 1,000 and you write 100. Is it correct? What if you wrote K? It's correct?
It's correct.
So if you are going to make a mistake in substitution, better push it right at the end. Because if you don't do that, everything you are writing is not correct. Do you understand that?
Yeah.
So try always to model everything in the symbols, because it's easier and the chances of making a mistake are less. So let's model it in what? In symbols. We are going to say restoring moment is equal to. There should be a minus. Does it make sense to put a minus? It should, no? Because if we are pulling it this way, this rotation. Now, when we are dealing with this, it's no longer upwards and downwards, ne? Or sometimes it's like this. So you can't say upwards. But this, if we call this one positive, that will be your acceleration. Then your spring will be pulling it this way. So it's still negative. Is that okay?
Yeah.
So to just summarize it, always your acceleration moment, or your acceleration whatever, force, moment, whatever, put that as positive. Then this must always act in the opposite direction, which means automatically it's a minus. The acceleration force is what? Kx. It's an x there. How do we make it a moment? We must multiply by the arm length, which is this. Okay?
Yes.
Because we are not just looking for the force. We want the moment. So this is the force.